The thermometer inside Ingrid Halverson's cabin read 42 degrees, while her neighbor's identical structure 300 yards away measured -16. The difference wasn't the stove, the wood, or the insulation. It was what lay hidden beneath her floorboards. Before we go further, let us know in the comments where you're watching from. And if stories of forgotten frontier ingenuity move you, subscribe. Because tomorrow's story might just change how you think about survival. The Dakota Territory. Winter of 1872 arrived early and without mercy. By mid-November, temperatures had already dropped below zero, and the wind that swept across the open prairie carried a cold that penetrated every gap, every crack, every imperfect seal in the hastily built homestead cabins scattered across the landscape. Ingrid Halverson stood at her cabin's single window, watching ice crystals form on the interior of the glass, despite the fire burning constantly in the cast-iron stove 15 feet behind her. She was 28 years old, a Norwegian immigrant who had arrived in America 4 years earlier with her husband Lars and dreams of land ownership that would have been impossible in the old country. They had claimed 160 acres under the Homestead Act, built their cabin in the spring of 1871, and survived their first winter through sheer determination and an enormous consumption of firewood. This second winter was proving harder. The cabin was well built by frontier standards. Lars had been a carpenter's apprentice in Stavanger before they emigrated, and he had applied those skills to their home. The logs were properly notched and chinked. The roof was solid. The door fit its frame with minimal gaps. They had even installed a real glass window, a luxury many homesteaders delayed for years. But none of that mattered when it came to heat distribution. Their stove sat against the north wall, a Detroit-made box stove they had purchased in Yankton for $42, nearly depleting their cash reserves. It burned wood efficiently and produced substantial heat. The problem was where that heat went. Within a 6-foot radius of the stove, the temperature was comfortable, even warm. Ingrid could stand there in her house dress without shivering. But 12 feet away, near the sleeping area where their daughter Karin's bed sat, the cold was oppressive. Ice formed in the water bucket overnight. Breath created visible clouds. The sleeping area was a different climate zone entirely. Ingrid had tried everything she could think of to improve the situation. She hung blankets from the ceiling to create a smaller heated space. She moved Karin's bed closer to the stove, but not too close for safety. She kept the fire burning through the night, waking every 2 hours to add wood. Lars had built an interior wall to partition off the sleeping area, thinking trapped heat would accumulate. It had made things worse by blocking what little warmth did circulate. They burned through firewood at an alarming rate. Lars spent 3 days each week cutting and hauling timber. Their woodpile, which should have lasted until March, was already half depleted by December. And still, Karin shivered under 3 wool blankets in her corner bed, coughing through the nights. Other families faced the same struggle. The Schneiders, 300 yards east, burned just as much wood with identical results. The Johnsons to the south had actually abandoned their cabin for the winter and moved into town, unable to keep their children warm. This was simply how frontier winters worked, everyone said. You endured, you survived, you waited for spring. Ingrid accepted this reality because she had no alternative. The engineering principles that might have solved the problem were unknown to her. The historical precedents that existed in other cultures were invisible on the Dakota prairie. She was a homesteader, not an inventor. But that was about to change. January 14, 1873, began like every winter morning. Ingrid woke before dawn to restart the fire that had burned down to coals overnight. The interior of the cabin was cold enough that her breath hung visible in the dim light from the banked embers. She added kindling, blew gently on the coals, and watched flames catch and grow. Within minutes, the area near the stove began warming. The far corners of the cabin remained frozen. Lars was already outside, breaking ice on the livestock water. Ingrid moved quietly, trying not to wake Karine, who had coughed through much of the night. The 4-year-old needed rest more than she needed an early breakfast. Ingrid set the coffee pot on the stove and waited for Lars to return. He came in stamping snow from his boots, his beard crusted with ice. They drank coffee in silence, both exhausted from weeks of inadequate sleep and constant cold. After 15 minutes, Lars noticed that Karine hadn't stirred despite the noise of his return and their conversation. Ingrid walked to her daughter's bed in the corner. Karine lay still under her blankets, her small face visible in the growing daylight from the window. Ingrid touched her forehead and felt heat that had nothing to do with the stove. Fever. High fever. They spent the day trying everything they knew. Ingrid bathed Karine's face with cool water. Lars rode 8 miles to the nearest neighbor who had medical experience, a former Army surgeon named Clayton. Clayton came immediately, examined Karine, and delivered his diagnosis with quiet certainty. Pneumonia. Advanced pneumonia. He left medicine and instructions, but his expression told Ingrid everything she needed to know. Children died from pneumonia regularly on the frontier. Medicine could help, but recovery depended largely on the child's constitution and the environment. Warmth, rest, and time were the real treatments. Clayton didn't say what they all understood. Karine had been sleeping in temperatures barely above freezing for weeks. Her body had been fighting constant cold exposure. The pneumonia had found a weakened opponent. Ingrid moved Karine's bed directly beside the stove, as close as safety permitted. She maintained the fire at maximum output, feeding it constantly. The space immediately around the stove became almost uncomfortably warm. Karine's fever continued climbing. For 3 days, Ingrid barely left her daughter's side. Lars kept the fire burning, brought water, prepared simple meals that neither of them ate. Neighbors came with food and offers of help that had no practical application. You couldn't cure pneumonia with casseroles or kind words. On January 17th, just after dawn, Karine stopped breathing. The fever had climbed through the night, despite everything Ingrid had done. The little girl simply slipped away, her body exhausted from fighting infection and cold simultaneously. Lars built a small coffin from boards he had been saving for spring furniture. They buried Karine in ground so frozen that digging the grave took 2 men an entire day. Ingrid stood at the graveside in temperatures 20 degrees below zero and understood with absolute clarity that her daughter had died not from pneumonia alone, but from living in a cabin that couldn't maintain survivable temperatures 15 feet from its heat source. The realization wasn't dramatic or sudden. It was cold, factual, and completely accurate. Lars contracted frostbite during the 2 days he spent digging Karine's grave in frozen ground. His hands blistered, then blackened at the fingertips. He wrapped them and continued working, caring for livestock and maintaining the fire, but the damage was done. Within a week, infection had set in. By early February, fever took hold. Clayton came again, with his medicine bag and his grim expressions. Infection from severe frostbite, especially when the victim continued working instead of resting, was frequently fatal. Lars lasted 9 days. He died on February 11, 1873, leaving Ingrid a widow at 28 with 160 acres of claimed land, a cabin, 4 cattle, 2 horses, and no family within 1,000 miles. The neighbors assumed she would abandon the claim and return to civilization. A woman alone couldn't maintain a homestead through spring planting and summer harvest, much less survive another winter. The sympathetic ones offered to help her arrange sale of her property and livestock. The opportunistic ones made offers to purchase the claim at fractions of its value. Ingrid refused every offer. She wasn't staying because of stubbornness or attachment to the land. She was staying because something had crystallized in her mind during the weeks between Karine's death and Lars's funeral, and that something demanded investigation. She had lost her family to cold, not to blizzards or exposure during travel, not to accidents or violence. They had died. Inside a well-built, properly maintained cabin that had a functioning stove burning constantly. The cabin had failed them. More specifically, the cabin's heating had failed them. Ingrid began measuring temperatures systematically. She purchased a thermometer from the general store in Yankton during a supply trip in late February. Back at the cabin, she recorded temperatures at different distances from the stove throughout the day and night. The data confirmed what she already knew experientially. 6 feet from the stove, temperatures averaged 55 to 60 degrees when the fire burned hot. 12 feet away, temperatures dropped to 35 to 40 degrees. 18 feet away, near where Karin's bed had been, temperatures barely exceeded 30 degrees even with maximum fire output. The same stove that created comfortable warmth in one small area left the majority of the cabin's interior at temperatures that would slowly kill anyone who slept there regularly. The heat was being produced. It simply wasn't reaching where it needed to be. Ingrid wasn't an engineer. She had received basic education in Norway, enough to read and calculate, but nothing in her background had prepared her to solve technical problems. What she did have was motivation born from loss, and the kind of focus that grief sometimes produces. She needed to understand why heat didn't spread and what could make it spread. Through March, as winter began its slow retreat, Ingrid spent hours observing her stove and the space around it. Heat rose, she knew that. Warm air moved upward and collected near the ceiling, but it didn't move outward effectively. The warmth concentrated in a column above the stove and gradually dissipated as it spread horizontally. By the time it reached the far walls, it had cooled to near ambient temperature. She needed a way to move heat horizontally before it could rise and dissipate. She needed a mechanism to transport warmth from the source to distant locations. The solution existed somewhere. She simply had to find it. The memory came unexpectedly in mid-March while Ingrid was repairing chinking between logs. She was thinking about her grandfather's farm outside Bergen, where she had spent childhood summers. The farmhouse had been old, built sometime in the 1700s, and it had possessed a peculiar feature she had never questioned as a child. The kitchen floor had always been warm, even in winter, even in rooms far from the cooking hearth. She sat back from her chinking work and focused on the memory. Her grandfather's kitchen had a large masonry hearth where her grandmother cooked, but the warmth didn't just radiate from that hearth into the immediate space. The floors throughout the main level of the house had been noticeably warm to bare feet. She remembered her grandmother explaining it once, though Ingrid had been too young to understand the significance. The chimney didn't go straight up. It traveled horizontally first, running beneath the floor in some kind of channel before turning upward and exiting through the roof. The hot smoke and gases from the cooking fire passed under the floorboards, warming them, before venting outside. The stone or brick channel that contained this horizontal chimney run absorbed heat and radiated it slowly upward through the floor. Ingrid stood and walked into her cabin, looking at her stove and its chimney pipe with new perspective. The pipe went straight up from the stove, through the roof, venting directly outside. All the heat that traveled up that pipe was lost. It warmed nothing but the open air above her cabin. What if the pipe didn't go straight up? What if it traveled horizontally first, running through or beneath the floor, warming the cabin's interior before finally venting? The principle her grandfather's farmhouse had used could work here, but the implementation would be different. Norwegian farmhouses were built on stone foundations with crawl spaces or cellars beneath. Her cabin sat directly on the earth with a simple plank floor over dirt. She would need to create channels beneath her floor. She would need to route the stovepipe through those channels. She would need to ensure the system could be cleaned and maintained. She would need to prevent fires, manage airflow, and solve a dozen technical problems she couldn't yet identify. The enormity of the project became clear as she thought through the requirements. She would need to excavate beneath her existing floor without undermining the cabin's foundation. She would need materials, pipe or ductwork, that could handle high temperatures. She would need to design a system that wouldn't fill her cabin with smoke if something failed. Most daunting, she would need to do all this alone. Lars had been the carpenter, the builder, the one with training and skill in construction. Ingrid could chink logs and make minor repairs, but digging trenches under an occupied building and installing a heating system was far beyond anything she had attempted. She spent 3 days thinking through the problems, making sketches, and considering whether the idea was even possible. The sensible decision would be to abandon the concept and simply accept that frontier cabins were cold. Thousands of homesteaders lived with the same conditions. Karin and Lars had been unlucky. She could survive future winters by burning more wood and sleeping closer to the stove, but sensible decisions hadn't saved her family. Standard practices had killed them. If standard cabin heating was inadequate, then something non-standard was required. On March 19th, Ingrid decided she would attempt what her memory had suggested. She would bring her grandfather's farmhouse heating principle to the Dakota prairie. She had no idea if it would work. She only knew she had to try. April brought thaw and mud and the first possibility of travel to neighboring homesteads. Ingrid used the improving weather to conduct research. She needed to understand how other people heated their cabins, what worked, what failed, and whether anyone had attempted solutions beyond the standard single-stove approach. Over 3 weeks, she visited every occupied homestead within 20 miles, using the pretense of neighborly visits to study their heating arrangements. The Schneiders had a cabin nearly identical to hers. Single cast-iron stove, central placement, constant fire through winter. Emma Schneider confirmed they burned through enormous quantities of wood and still suffered freezing temperatures in the sleeping areas. Their youngest child had developed a persistent cough that lasted all winter. Emma accepted this as normal. The Johnsons had tried a different approach. They had installed 2 smaller stoves, one for cooking and heating the main room, another in the sleeping area. This had required 2 chimneys and doubled their wood consumption while providing only marginal improvement. The sleeping area stove had to be tended through the night, or temperatures dropped dangerously. They had abandoned this system after one winter. A German family named Kruger had built their cabin with a central fireplace instead of a stove. The fireplace was beautiful stonework and provided excellent heat to the immediate area, but it consumed even more wood than stoves and heated less efficiently. Most of the heat went straight up the chimney. Every cabin Ingrid visited had the same fundamental problem. Heat was produced at a single point and radiated outward with rapid temperature drop over distance. No one had solved distribution. No one had even seriously attempted to solve distribution. The accepted wisdom was that frontier cabins were cold, and you adapted by wearing more clothing, using more blankets, and burning more wood. Ingrid also noticed that most homesteaders had minimal understanding of heat behavior. They knew fire was hot and that hot air rose, but the mechanics of heat transfer, thermal mass, and convection were mysteries. When she asked careful questions about why heat didn't spread, she received answers that ranged from vague to completely incorrect. One conversation proved particularly useful. Anders Paulsen, a Norwegian bachelor who had filed his claim in 1869, mentioned that he had worked briefly in a Minnesota sawmill before homesteading. The sawmill had used a system of metal ducts to move warm air from a large furnace to different areas of the building. The ducts were simple sheet metal tubes that carried heated air horizontally before releasing it through vents. Anders had no detailed knowledge of how the system worked, but the basic concept was clear. Heat could be transported through enclosed channels. This aligned with Ingrid's grandfather's farmhouse, where the chimney channel had moved heat horizontally. The principle was consistent. Enclose heat in a duct or channel, move it to where you need it, release it, or allow it to radiate through the channel. Walls. Ingrid returned home in late April with confirmation that no one locally had solved cabin heating, and that the basic principle she remembered from Norway had industrial applications she hadn't known about. The system she imagined was possible. She simply needed to figure out the specific implementation for her circumstances. In early May, Ingrid made a supply trip to Yankton, the nearest substantial town 40 miles southeast of her claim. The trip required 2 days of travel with an overnight camp, but she needed staples and wanted to investigate whether any materials existed that could serve as heat ducts in her planned system. She had some money remaining from selling Lars's tools and some of their furniture to neighbors. She intended to spend it carefully. Yankton, in 1873, was a rough frontier town serving as a supply point for homesteaders, miners, and the occasional military expedition. Ingrid visited the general store, the blacksmith, and a building supply yard that served construction projects in the region. None had anything resembling what she needed. Metal pipe was available, but only in small diameters meant for water or stovepipe in standard straight sections. Sheet metal could be purchased, but forming it into ductwork would require skills and tools she didn't possess. Discouraged, she prepared to return home. On her way out of town, she passed an area where the remains of an abandoned mining operation sat, slowly rusting. The mine had been an optimistic venture that had failed after 2 years when promised ore deposits proved non-existent. The buildings were collapsing, and most valuable equipment had been salvaged, but debris remained scattered across several acres. Ingrid walked through the ruins, not looking for anything specific, simply delaying her departure. Behind a collapsed shed, she found a pile of corrugated metal tubing, partially buried in weeds and dirt. She pulled a section free and examined it. The tubing was flexible, made from thin metal formed into a ribbed pattern that allowed it to bend while maintaining an open channel. Each section was about 8 feet long and 12 inches in diameter. The metal showed rust but remained structurally sound. She had no idea what the tubing's original purpose had been. Mining operations used all manner of specialized equipment, but she recognized immediately that this material could work for her heating system. The flexibility would allow her to route it around obstacles. The diameter was large enough to carry substantial airflow. The corrugated design provided surface area for heat radiation. Ingrid counted 14 sections of tubing in various states of preservation. She loaded 8 of the best sections onto her wagon, along with several loose metal brackets and fasteners she found scattered nearby. No one stopped her. The mine was abandoned, the equipment worthless scrap. She was welcome to whatever she could haul away. The return trip took 3 days because the tubing was awkward to transport. When she finally reached her cabin, she unloaded the sections and laid them out for inspection. 6 were in excellent condition. 2 had damaged areas that would need repair or sealing. All were functional enough for her purposes. She had her ductwork. Now she needed to determine exactly how to install it, where to route it, and how to connect it to her stove in a way that would move heat without creating a fire hazard or filling her cabin with smoke. The engineering challenges were substantial, but they were no longer theoretical. She had materials and a clear goal. Through late May and into June, Ingrid designed her system on paper using charcoal and sheets of brown wrapping paper spread across her table. She drew the cabin's footprint from above, marking the stove's location and the areas that needed heating most desperately. The sleeping area where Corinne's bed had been was the priority. The far corners where temperature dropped most severely were secondary targets. She sketched various duct routing options. Her first idea was to run a single main duct from the stove to the far wall, but this would heat only a narrow corridor. Her second idea was to create a branching system like tree roots, but the complexity seemed overwhelming, and she lacked enough ductwork. Her third design was simpler and more elegant. 4 ducts radiating outward from the stove area in a cross pattern, running beneath the floor to each wall, creating 4 zones of radiant heat. The ducts would need to be buried in trenches dug into the earth beneath her floor. The trenches would need to be deep enough that the floorboards could be reinstalled above them with sufficient clearance. She estimated 18 inches would work, giving her room for the 12-inch diameter duct, plus space for airflow and maintenance access. The critical engineering problem was connecting the ducts to her stove without creating a chimney backup. Stove draft depended on hot gases rising through the vertical chimney pipe. If she diverted those gases horizontally into her duct system, she might kill the draft and cause smoke to pour into the cabin. She needed a way to split the flow, sending some heat into the ducts while maintaining adequate draft through the main chimney. Ingrid spent days thinking through this problem. Her solution was to modify the stove's chimney collar, the fitting where the pipe attached to the stove top. She would create a plenum chamber, a box that would sit on top of the stove and collect hot gases. From this plenum, one pipe would continue upward as the main chimney. 4 smaller openings would connect to her underground ducts. The rising heat would naturally flow in all directions. Most would still go up the chimney, maintaining draft, but a portion would be diverted into the duct system. She had no formal training that told her this would work. She was reasoning from basic principles and intuition. Hot air rises and spreads. If you give it multiple paths, it will take all of them in proportion to their resistance. A large vertical chimney would take most of the flow. Smaller horizontal ducts would take less, but enough to carry useful heat. The remaining design questions involved practical details. How deep should the trenches be? How would she support the floor above them? What would line the trenches to prevent collapse? How would she seal the duct connections? How would she access the system if something needed repair? Ingrid answered each question methodically. 18-inch trenches. Floors supported on crossbeams spanning the trenches. Trenches lined with river stone for stability and thermal mass. Duct connections sealed with the same clay mixture she used for chinking. Access provided by making certain floor sections removable. By mid-June, she had a complete plan drawn out and a list of additional materials she would need. The plan looked possible. Whether it would actually work remained unknown. Ingrid began excavation on June 22, 1873. She started by removing floorboards from a section near the stove, prying them up carefully to avoid splitting the wood. Each board was numbered with charcoal marks so she could replace them in exact order. The floor came up more easily than she had expected. Lars had built it to be serviceable, with boards laid across supporting joists rather than nailed permanently. Beneath the boards, she found packed earth, dry and hard from years of compressed settlement. She marked her first trench line using stakes and string, creating a straight path from the stove area toward the east wall. The trench would be 18 inches deep and 14 inches wide, slightly wider than the duct diameter to allow for stone lining. Digging was brutal work. The earth was dense clay mixed with rocks. Ingrid used a mattock to break the surface, then a spade to remove loosened material. Her hands blistered within the first hour. She wrapped them with cloth strips and continued. Progress was measured in inches. By the end of the first day, she had excavated 3 feet of trench to the required depth. The physical demands were compounded by the confined space. She was working inside her cabin, bent over, swinging tools in limited clearance. Ventilation was poor. Dust filled the air with every mattock strike. She developed a rhythm. 30 minutes of digging, 10 minutes of rest and water. She removed excavated earth in buckets, carrying it outside and dumping it in a growing pile beside the cabin. Neighbors noticed the activity. Emma Schneider stopped by on the 3rd day, ostensibly to bring bread but clearly curious about what Ingrid was doing. She found the interior of the cabin torn apart, trenches carved into the floor, dirt everywhere. Ingrid explained she was installing a heating system based on principles from Norwegian farmhouse construction. Emma listened politely, her expression skeptical, and left quickly. Within a week, everyone within 10 miles knew that the widow Halverson had lost her mind and was destroying her cabin's floor. Ingrid ignored the gossip. She had 4 trenches to dig, each running from the central stove area to a different wall. The east trench took 6 days to complete at 12 feet long. The west trench took 5 days, benefiting from her improved technique. The north and south trenches each took 4 days. By late July, she had a cross-shaped pattern of trenches carved into her cabin floor, totaling 48 feet of excavation. The cabin looked like a construction disaster. Floorboards were stacked along the walls. trenches cut through the interior like small canyons. Dirt covered every surface, but the hardest physical labor was complete. Ingrid stood in the center of her torn-apart home, sweating and exhausted, looking at the pattern she had created. The trenches were straight, properly dimensioned, and ready for the next phase. She allowed herself one evening of rest, then began gathering river stones. The nearest river was 1.5 miles from Ingrid's cabin, a small tributary that ran year-round and had carved a shallow bed through the prairie. The riverbed was full of smooth stones, worn round by water flow over centuries. These stones were what Ingrid needed to line her trenches, creating a stable thermal mass that would absorb heat from the ducts and radiate it upward through the floor. She made her first trip to the river on August 2nd, pulling a small handcart Lars had built for hauling supplies. The cart could carry perhaps 200 pounds of stone. She spent 3 hours selecting and loading stones of appropriate size, roughly the dimensions of her fist or slightly larger. Smaller stones would shift and settle. Larger stones would be difficult to fit and arrange. She wanted uniformity. The return trip, pulling the loaded cart across prairie grass and uneven ground, took nearly 2 hours. She arrived home exhausted, unloaded the stones, and realized she had enough material to line perhaps 6 feet of trench. She would need 15 to 20 more trips to complete the work. Over the next 3 weeks, Ingrid established a routine. Rise at dawn, make the trip to the river, spend 2 to 3 hours selecting and loading stones, haul the cart home, unload, rest, then spend the afternoon placing stones in the trenches. She made the trip 18 times, hauling nearly 2 tons of river stone, 1 cartload at a time. The stone placement required care. She started at the bottom of each trench, laying stones to create a flat, stable base. Then, she built up the walls, placing stones in interlocking patterns that would resist shifting. She left a channel in the center where the duct would sit, supported by the stone walls on either side. The work was like building very small, very low walls inside narrow ditches. As she worked, she mixed mortar using clay she dug from a deposit near the river, mixed with sand and water. The mixture wasn't as strong as lime mortar, but it was adequate for her purposes. She applied mortar between stones, filling gaps and creating a somewhat sealed channel. The mortar would also help the stone mass act as a unified heat sink rather than individual loose rocks. By late August, all 4 trenches were lined with stone. The cross pattern beneath her floor now consisted of rock-walled channels, each about 12 inches wide and 14 inches deep from floor level to the stone base. The channels were straight, solid, and ready to receive the metal ductwork. Ingrid stepped back and assessed the work. 3 months had passed since she had begun this project. She had excavated trenches, hauled tons of stone, and transformed her cabin's interior into something unrecognizable. The physical toll was evident. She had lost weight. Her hands were permanently calloused. Her back ached constantly. But the foundation of her heating system was complete. Now came the technical challenge of installing the ducts and connecting them to the stove without burning down her cabin. The ductwork installation began on September 5th. Ingrid laid out her 8 sections of corrugated metal tubing, examining each for damage and planning how to cut and fit them into her trench system. Each section was approximately 8 feet long. Her trenches averaged 12 feet, meaning she would need to connect multiple sections using overlapping joints. She started with the east trench, the longest at 12 feet. She positioned one 8-foot section of duct in the stone-lined channel, supporting it on small stone pillars she had built to keep the metal slightly elevated above the trench bottom. This elevation would allow air circulation beneath the duct and prevent moisture accumulation. She then cut a 4-foot section from another duct using tin snips, a tool she had borrowed from the blacksmith in Yankton on her last supply trip. Connecting the sections was problematic. The corrugated design meant the ends weren't smooth. She couldn't simply slide one section into another. Her solution was to flatten the last few inches of corrugation on one piece, creating a smooth sleeve, then fit the next section inside this flattened area. She wrapped the joint with wire to hold it firm, then sealed it with a mixture of clay and ash paste that would harden when heated. The same process was repeated for each trench. West Trench received one full section plus a 4-foot extension. North and South Trenches each got similar treatment. By September 10th, all 4 trenches contained installed ductwork running from the central stove area outward to the cabin walls. The critical engineering challenge was creating the plenum chamber that would sit atop the stove and distribute heat into the ducts while maintaining chimney draft. Ingrid designed a simple box using sheet metal she had purchased in Yankton. The box would be 18 inches square and 12 inches tall, sitting directly on the stove's flat-top surface. She couldn't fabricate the plenum herself. The work required soldering and metal shaping beyond her skill. She took her design drawings to the Yankton blacksmith, a Swedish immigrant named Torsten, who had done repair work for Lars in the past. Torsten studied the drawings, asked several questions about what she was trying to accomplish, and agreed to build the plenum for $8. She returned a week later to find Torsten had created exactly what she had specified. The metal box had 5 openings. One large opening on top would connect to the main chimney pipe. 4 smaller openings on each side would connect to the underground ducts. The construction was solid, with seams properly sealed to prevent smoke leakage. Back at her cabin, Ingrid installed the plenum by placing it on the stovetop and sealing the base with stove cement. She connected the main chimney pipe to the top opening. Then came the moment of truth. She needed to connect the 4 underground ducts to the plenum's side openings. This required cutting access holes through her cabin floor directly adjacent to the stove and running short vertical sections of duct from the horizontal underground runs up into the plenum openings. The connections had to be airtight or smoke would leak into the cabin. She worked methodically, cutting floor access, fitting vertical connectors, sealing every joint with her clay paste mixture. The work took 2 full days. With the ductwork installed and connected to the plenum chamber, Ingrid faced a structural challenge she had been postponing. The floor needed to be restored over the trenches, but the restoration had to allow for several requirements. The floor must support weight, allow heat radiation from the buried ducts, provide access for maintenance, and not shift or settle over time as the earth beneath compacted. Her original floorboards couldn't simply be laid back across the trenches. The gaps were too wide and lacked support. She needed to create a framework that would span the trenches while leaving the duct channels open beneath. Her solution was to build crossbeams perpendicular to each trench at 3-foot intervals, creating a support structure that bridged the gaps without blocking the channels. She used lumber she salvaged from an old shed Lars had built and partially dismantled before his death. The beams were notched to rest on the stone-lined trench walls, distributing their weight onto the stable masonry rather than the earth between trenches. Each beam was 6 inches wide and 2 inches thick, strong enough to support floorboards and foot traffic. Installing these crossbeams required precision. If they sat too low, they would compress the ducts. If they sat too high, the floor would be uneven. She used a level and careful measurement to ensure each beam sat at exactly the right height, flush with the original floor joists that remained in areas without trenches. Once the crossbeams were in place, she reinstalled the floorboards using the numbering system she had created during removal. Most boards went back exactly as they had been, but in certain strategic locations above the trenches, she modified the installation. Instead of nailing these boards permanently, she attached them with removable wooden pegs fitted into drilled holes. These sections could be lifted out if she ever needed to access the ductwork for cleaning or repair. The removable sections weren't obvious to casual observation. The boards fit tightly and looked identical to permanently installed sections, but Ingrid knew which boards were removable and could access any part of her underground heating system within minutes by pulling the appropriate section. By September 23rd, The floor was completely restored. The cabin's interior looked nearly normal again, though cleaner than it had been in months due to Ingrid's obsessive sweeping and cleaning during the final assembly phase. The only visible evidence of the heating system was the plenum chamber sitting on top of the stove and the slightly modified chimney configuration. Standing in her restored cabin, Ingrid felt both anticipation and dread. 3 months of brutal physical labor had been invested in a system that existed nowhere else, designed by someone with no formal engineering training, based on childhood memories and improvised solutions. Whether it would work, whether it would heat her cabin, or fill it with smoke and fire, would be determined the moment she lit the stove and tested the complete system for the first time. Ingrid chose September 25th for the initial test. The weather was cool enough to justify a fire, but not yet cold enough that failure would be catastrophic. She wanted to observe the system under controlled conditions before depending on it for survival. She spent the morning preparing, checking every connection, examining every seal, and ensuring the main chimney pipe had clear draft. At noon, she built a small fire in the stove using dry kindling and a few pieces of split oak. She left the stove door slightly open to observe the flames and ensure proper combustion. The kindling caught easily. Flames grew. She added larger pieces of wood and closed the door, adjusting the draft control to moderate the burn rate. Smoke rose from the chimney outside. Inside the cabin, no smoke appeared. The initial draft was functioning correctly. Heat began radiating from the stove's iron surface, as it always had. But now heat was also being diverted into the plenum chamber and down into the underground duct system. The question was whether that heat would travel through the ducts, warm the stone channels, and radiate upward through the floor without creating problems. Ingrid sat at her table and waited. After 15 minutes, she walked to the east wall where the first duct terminated beneath the floor. She knelt and placed her palm on the floorboards. They were slightly warm, noticeably warmer than the ambient cabin temperature. The heat was traveling. She checked the west wall. Same result. Warm floorboards above the buried duct, north wall, south wall, both showed temperature increase. The system was distributing heat. She returned to the stove area and checked the floor directly above the duct connections where they entered the plenum. The boards there were quite warm, almost hot. Heat was definitely flowing into the underground network. Over the next hour, she monitored temperatures throughout the cabin. The area immediately around the stove warmed quickly, as expected. But unlike previous winters, the warming didn't stop at a 6-foot radius. The floor across the entire cabin was becoming noticeably warmer. The difference was subtle at first, but it was real and measurable. By mid-afternoon, 3 hours after lighting the fire, Ingrid used her thermometer to take measurements. 6 feet from the stove, the air temperature was 58 degrees. At the east wall, 12 feet from the stove, the air temperature was 51 degrees. The temperature differential was only 7 degrees across the entire cabin length, compared to the 25 to 30 degree differentials she had experienced in previous winters. More importantly, the floor temperature was nearly uniform throughout the cabin. Standing barefoot on the boards above the buried ducts felt noticeably warm. The radiant heat from below was creating a comfortable environment that didn't depend entirely on hot air circulation. The system worked. Heat was being distributed, the cabin was warming evenly. No smoke had entered the living space. The chimney draft remained adequate. Ingrid's 3 months of labor had produced a functional heating system that solved the exact problem she had set out to address. The initial success revealed several problems that required solutions. The most significant issue was heat escaping too quickly through certain sections of duct. The east and west runs, which were longest, showed diminishing warmth at their far ends. Heat was radiating through the duct walls before reaching the terminal sections, leaving the most distant areas of the cabin underheated. Ingrid's solution was selective insulation. She removed floor sections above the first half of each long duct run and packed earth tightly around the metal tubing in those areas. The packed earth insulated the duct, forcing heat to travel farther before radiating outward. The far ends of the ducts, where she wanted maximum heat radiation, remained exposed in their stone channels with airspace around them. This modification required a week of work, carefully packing clay-rich earth around specific duct sections while leaving others exposed. The result was improved heat distribution. The terminal areas of all 4 duct runs now received adequate heat, creating more uniform floor temperatures throughout the cabin. The second problem involved draft control. On particularly windy days, strong winds created powerful chimney draft that pulled heat too quickly through the system. The fire burned hotter than necessary, consuming wood rapidly, while sending too much heat up the chimney rather than into the ducts. Ingrid needed a way to regulate how much heat went into the underground system versus up the main chimney. Her solution was adding simple dampers. She fabricated metal plates that could slide partially across the duct openings in the plenum chamber, restricting flow into the underground system when desired. By adjusting these dampers, she could control the heat split between chimney and ducts, optimizing efficiency for different weather conditions and heating demands. The dampers were crude, just flat pieces of tin mounted on wire pivots, but they were effective. On cold, calm days, she opened the dampers fully, sending maximum heat into the floor system. On windy days, or when she needed less heating, she partially closed the dampers, reducing underground heat flow and preventing waste. A third refinement involved moisture management. During a rainy period in October, Ingrid noticed slight condensation forming in the trenches where temperature differentials between the warm ducts and cool earth created conditions for water vapor to condense. The moisture wasn't immediately problematic, but over time it could cause rust and deterioration. She addressed this by improving ventilation in the stone channels. She drilled small holes through the floor at the terminal ends of each duct run, creating passive vents that allowed air circulation. Moist air could escape, dry air could enter, and the system remained dry even during humid conditions. By late October, after 5 weeks of observation and modification, Ingrid had refined her heating system to near optimal performance. The cabin maintained comfortable temperatures with approximately 60% of the wood consumption she had burned in previous winters. Temperature variation from warmest to coolest areas was less than 10 degrees. The floor was warm throughout, creating radiant comfort that standard stove heating never achieved. The system was ready for winter. The first heavy cold arrived in early November, bringing temperatures well below zero and wind that cut across the prairie like blades. Ingrid's cabin maintained a steady internal temperature of 42 degrees, with a moderate fire burning during daylight hours and banked coals overnight. Her neighbors, burning fires constantly, struggled to keep their cabins above freezing in the sleeping areas. On November 9th, a traveling Methodist preacher named Reverend Thomas Clayton stopped at Ingrid's cabin seeking shelter for the night. Circuit preachers traveled between scattered homesteads bringing religious services and news. They depended on frontier hospitality and were rarely turned away. Ingrid welcomed him, offered a simple meal, and prepared her sleeping area for his use while she would take blankets near the stove. Clayton entered the cabin grateful for any warmth. Within minutes, he noticed something unusual. The entire interior felt comfortable, not just the space near the stove. He walked to the far corner, the area Ingrid indicated was the sleeping space, and was astonished to find it genuinely warm. He knelt and placed his hand on the floor. The boards radiated heat. He asked Ingrid how this was possible. She explained her underground duct system, the stone-lined channels, the plenum chamber, and the 3 months of construction. Clayton listened with the attention of a man who had spent countless nights in freezing frontier cabins. He asked to see the system. Ingrid lifted one of the removable floor sections, revealing the stone channel and the metal duct glowing faintly with conducted heat. Clayton spent that night in comfort he hadn't experienced since leaving established towns in the east. The sleeping area was warm enough that a single blanket was adequate. He slept deeply and woke refreshed rather than stiff and cold. Before departing the next morning, he asked permission to tell others about what he had seen. Ingrid granted it freely. Over the following weeks, Clayton visited 11 homesteads on his circuit. At each, he described Ingrid Halverson's heating system with the enthusiasm of a man who had witnessed something genuinely innovative. He told farmers, trappers, and other settlers about the underground ducts, the warm floors, and the dramatic reduction in wood consumption. Some listeners dismissed the account as exaggeration, others were intrigued. By December, a steady stream of visitors began appearing at Ingrid's cabin. Homesteaders traveled miles to see the system for themselves. She welcomed them, explained the principles, showed the installation, and answered questions. Some visitors were merely curious, others took careful notes, asked detailed questions about construction methods, and clearly intended to replicate the system. Emma Schneider came in mid-December, no longer skeptical but genuinely interested. She apologized for her earlier doubts and asked if Ingrid would help her husband install a similar system in their cabin. Ingrid agreed. The widow, who neighbors had thought insane, was becoming a consultant on heating technology, teaching principles she had learned through necessity and implemented through determination. Winter arrived with exceptional severity. The cold that descended on the Dakota Territory in late December 1873 was the worst in recorded memory for the region. Temperatures dropped to 30 below zero and stayed there for days. Wind created conditions that felt even colder. Snow fell intermittently, but the primary threat was the sustained, brutal cold that tested every structure and killed livestock caught without adequate shelter. Ingrid's cabin faced the same conditions as every other homestead. The difference was her heating system. She maintained her fire at moderate levels, burning through perhaps 12 pieces of split wood per day. The underground ducts distributed heat efficiently enough that the cabin's interior remained at 42 degrees even as outside temperatures reached -35. Her thermometer readings showed remarkable consistency. Morning temperature before rebuilding the fire, 38 degrees. Midday temperature with moderate fire, 44 degrees. Evening temperature, 42 degrees. The thermal mass of the stone-lined channels was absorbing heat during peak fire periods and releasing it slowly during low fire periods, creating temperature stability that single-point stove heating could never achieve. 3 homesteads within 5 miles experienced catastrophic heating failures during this cold period. The Johnson family's dual stove system consumed their entire remaining woodpile in 8 days. They abandoned their cabin on January 4th and moved in with relatives 20 miles south. The Kruger family's fireplace developed a chimney blockage from ice formation. They spent 2 days burning minimal fires while trying to clear the blockage, during which their interior temperature dropped below zero and water supplies froze solid. Most tragically, a family named Patterson, who had claimed land in September, suffered multiple frostbite injuries. Their hastily built cabin had inadequate chinking and a small, inefficient stove. The father lost 3 toes. One child developed severe frostbite on both hands. They survived only because a neighbor found them in critical condition and transported them to Yankton for medical care. Ingrid heard these stories through the informal communication network that connected scattered homesteads. Each account reinforced her understanding of how close she had come to similar disasters in previous winters. Her system hadn't just improved comfort, it had created a genuine survival advantage. On January 12th, during a brief warming period that brought temperatures up to zero, Anders Paulson arrived at Ingrid's cabin, leading 4 other men. They were homesteaders from claims within 15 miles, all desperate for heating solutions. They asked if Ingrid would teach them her system. They would pay for her time and expertise. Ingrid named a price of $5 per installation consultation, to be paid in cash or equivalent goods. All 5 men agreed immediately. She spent the remainder of January visiting their cabins, assessing their structures, explaining the principles, and helping them plan installations. Not all cabins were suitable for underground duct systems, but most could accommodate modified versions. The work kept her busy and provided income that would help her maintain the homestead through the coming year. The men who had mocked Ingrid's project most openly during the previous summer were among the first to request her help with heating installations. Heinrich Müller had been particularly vocal, telling anyone who would listen that the widow was wasting time and money on foolishness when she should be preparing for practical survival. His cabin, built with traditional methods and heated with a standard stove, had proven barely inhabitable during the extreme cold. Müller appeared at Ingrid's door in late January with his hat in his hands and a request for consultation. He offered $10, double her stated rate, if she would prioritize his installation. Ingrid agreed without mentioning his previous ridicule. She needed the money, and dwelling on past insults served no purpose. She spent 3 days at Müller's cabin, designing a modified system that worked within his structure's limitations. His cabin was smaller than hers and built directly on the ground without the raised floor that had made her installation easier. She adapted by creating shallower trenches and using smaller diameter ductwork. The system wouldn't be as efficient as hers, but it would provide significant improvement over his current situation. Müller worked alongside her, digging trenches and hauling stone under her direction. He was a large man, physically strong, and the labor went faster than Ingrid's solo work had proceeded. During the 3 days, he apologized twice for his earlier comments. Ingrid accepted the apologies without elaboration. Actions mattered more than words. Müller was paying her, following her instructions, and learning her techniques. That was sufficient. The second installation she supervised was for the Schneider family. Emma's husband Otto was a careful, methodical worker who asked intelligent questions and took detailed notes. His installation proceeded smoothly. By mid-February, the Schneider cabin had a functional underground heating system that reduced their wood consumption by half while dramatically improving comfort. Word continued spreading beyond the immediate area. By March, Ingrid had consulted on 9 installations within a 20-mile radius. She had earned $62 more cash money than she had seen since arriving in Dakota territory. The work was physically demanding and time-consuming, but it was also validating. Her system worked. Others recognized its value. The innovation born from tragedy was saving resources and potentially lives across the scattered homesteading community. Not everyone adopted the technology. Some homesteaders lacked the physical capability to undertake the installation work. Others couldn't afford materials or Ingrid's consultation fee. A few remained skeptical despite evidence, convinced that traditional methods were adequate. But among those who understood the principles and possessed the means, adoption was rapid. The phrase Halverson heating began appearing in conversations. Homesteaders would ask each other if they had installed Halverson heating or whether they planned to before next winter. The term wasn't formal or official. It emerged organically from people who needed a name for the innovation. They were witnessing and adopting. As more homesteaders installed underground heating systems, variations began appearing based on available materials and individual circumstances. Ingrid encouraged experimentation. Her design had solved her specific problem, but she recognized that different conditions might benefit from different approaches. The core principle remained constant: distribute heat through underground channels before it could escape the structure. The implementation details were adaptable. A German homesteader named Friedrich Weber created a variation using clay drainage pipe instead of metal ductwork. The pipes were heavier and more brittle, but also cheaper and locally available from a pottery works in Yankton. Weber installed his system in April and reported good results. The clay pipes conducted heat less efficiently than metal, but retained heat longer, creating more stable temperature patterns with less fluctuation. The Johnsons, who had returned to their cabin after the brutal winter, installed a double-layer system. They created shallow trenches only 12 inches deep, but ran 2 parallel ducts in each trench, one above the other. The upper duct vented to the outside after distributing heat. The lower duct recirculated air back toward the stove using natural convection. This created a continuous circulation loop that moved more total heat than Ingrid's single-duct design, though it required more complex construction. Anders Paulsen developed an innovation that addressed smoke management. He installed a water jacket around his stove's plenum chamber, creating a heat exchanger that warmed water while capturing heat for the duct system. The heated water could be used for washing and cooking, adding utility beyond space heating. Several other homesteaders adopted this modification. These variations were shared freely. Homesteaders visited each other's cabins, examined different installations, and borrowed ideas. An informal knowledge network developed where successful innovations spread rapidly, while failed experiments were noted and avoided. Ingrid participated in this network, learning from others' modifications even as they had learned from her original design. By summer of 1874, underground heating systems existed in approximately 30 cabins within a 50-mile radius of Ingrid's homestead. The density was highest among Scandinavian and German immigrant communities, where traditions of efficient heating and practical engineering were cultural values. But the technology crossed ethnic boundaries. Anyone who understood the principles and possessed the capability to install the system could benefit. The variations also revealed limitations. Very small cabins didn't benefit enough to justify the installation effort. Cabins built on rocky ground where trench digging was impractical couldn't accommodate the system. Temporary structures occupied for only one season weren't worth the investment. But for permanent, homesteads occupied by families planning to stay long-term, underground heating became an increasingly standard feature rather than an exotic innovation. The frontier was adapting, incorporating new knowledge into its building practices. Ingrid Halvorsen lived on her Dakota homestead until 1901, when declining health forced her to move to Yankton to live with her niece's family. She was 56 years old and had survived 28 winters in the cabin she had modified with her heating system. The system functioned reliably for the entire period, requiring only minor maintenance and occasional duct cleaning. She never remarried after Lars's death. She maintained her claim, raised cattle and chickens, and lived a quiet, self-sufficient life. The income from heating system consultations in the mid-1870s had provided capital that she invested in livestock and equipment. By the 1880s, she was one of the more prosperous single women in the territory, respected for both her practical skills and her pioneering heating innovation. Ingrid died in Yankton in 1909 at age 64. Her obituary in the local newspaper mentioned her as a homesteading pioneer, but made no reference to her heating innovation. To the broader world, she was simply another immigrant woman who had survived the frontier era. Her cabin was sold with the land and occupied by new owners who appreciated the warm floors without fully understanding the engineering beneath them. The heating system continued functioning for decades after her death. The cabin changed hands several times through the early 1900s. Each successive owner benefited from the underground ducts and stone channels that Ingrid had installed 40 years earlier. The system required no significant repairs. In 1983, archaeological researchers from the University of South Dakota conducted a survey of abandoned homesteads in the region. When they excavated the site of Ingrid's cabin, they discovered the underground heating system intact beneath the collapsed structure. The stone-lined channels were clearly visible. Sections of corrugated metal ductwork remained in place, rusted but recognizable. The researchers discovered evidence of similar systems in 47 other abandoned homestead sites across South Dakota, North Dakota, and Nebraska, all dated from the 1870s through the 1890s. Documentary research connected these sites to immigrant communities and traced the knowledge network back to the area where Ingrid Halvorsen had homesteaded. The academic paper published in 1986 identified Ingrid as the likely originator of the underground heating technique and noted that her innovation had spread across a significant geographic area. The paper estimated that the heating systems reduced wood consumption by 40 to 60% compared to standard single-stove heating. Today, Ingrid's original homestead site is unmarked grassland, but beneath the soil, stone channels remain arranged in a cross pattern, silent testimony to one woman's response to unbearable loss. Her solution required no new technology, only existing materials used with intelligence and determination. It worked for decades, spreading across the frontier through voluntary adoption by people who recognized genuine improvement. A cabin floor that radiated heat from corner to corner wasn't magic. It was engineering, implemented by a woman who refused to accept that traditional methods were the only methods, proving that innovation could emerge from tragedy and create warmth where cold had previously killed.